Okay, welcome everyone. Welcome to another Common Lisp study group. I'm your host, Ron Batum with Atlanta Functional Programming. Today we're going to be discussing a library that, really I've been recently exploring, the FSet library. This kind of fits into AFP's kind of moniker of trying to promote functional programming. And it's really a pretty well-versed library that I thought should get highlighted here at the Common Lisp study group. So I'm still going through some of the tutorial stuff, but I'm going to try and explain what I found so far, some of the concepts that it tries to embrace, as well as some of the base data structures that are provided by this library as well. But first, I think it's necessary just for folks who are just starting out with Common Lisp and coming in from other languages, particularly other Lisps like Clojure or Scheme. Why does a explanation is needed to understand why Common Lisp needs a library like this? So in the past, I've highlighted, and this study group has highlighted the fact that Common Lisp, while having many functional features and tries to promote kind of a functional programming style to programming, at its heart, a lot of its core data structures still allow mutable operations, which is somewhat antithetical to the functional programming kind of characteristics that most people are familiar with, mainly immutability, first-class functions, and so forth. So, but does that mean that you can't do functional programming with just base data structures? Actually, that's not true. Most of the Common Lisp libraries functions can work functionally on top of, at the very least, list-based data structures. That is, data structures that are built using cons. Consoles are obviously a native portion of Common Lisp and Lisps in general, and it was a important design decision by the Common Lisp community to have a set of library functions that work on such Lisp-based structures in an immutable fashion and in a shared-based fashion, because obviously that would allow, at the time when the standard was being built, there were certain system-oriented Lisps that were optimized to actually run on hardware. And some examples of this is Symbolics, Lisp, Genera. But when the standard was created and after it was created, these notions and functions and APIs that were associated with Lisp-based structures, while they worked well with those structures to work functionally there, they didn't necessarily work well with some other data structures that most people are kind of using on a day-to-day basis, mainly things like sets and maps. So there was a need and a gap that was necessary in order for us to, be able to write code in somewhat a functional style inside Common Lisp itself, and that's where libraries like FSet comes in. Now, are there other data structure libraries that provide something similar? There are a bunch of them, and I think in the coming weeks, my plan is to actually show some of these to you. Up until then, I encourage for folks who are interested in wondering what those kinds of libraries are to go head over to AwesomeCL, which is a GitHub markdown language written by one of our Common Lispers that kind of lists out a bunch of interesting libraries that might be helpful to you, in which there's a specific section dedicated to data structures itself. I'll post a link in the YouTube video description once we're done here. But let's get started on understanding FSet itself. The first thing to note is what FSet provides and what is its ultimate goal. And its goal is trying to create a collection library for Common Lisp that has a bunch of immutable collections. It tries to do this in as optimal a way as possible, but obviously, as you work through the code, things might fall through the cracks, and the design is constantly being improved. So there are a couple of concepts that I think need to be brought to light before we start getting into actual code. One thing is understanding that when it comes to using functional libraries and actually addressing performance, especially in runtime characteristics of a functional program, understanding that every operation has some sort of time complexity dealing with making sure that it preserves the immutable properties necessary. So a lot of these interfaces and a lot of the data structures were built to try to maintain some sort of acceptable time complexity. So obviously it's not going to be as fast as, say, maybe something that if you just allow a few mutations and a few mutable operations, the actual overall runtime code will be faster. But it will be fast enough for you to be able to use it in a real-world programming scenario. So that's one thing that you need to at least take a look at when you are exploring this library and some of its collections. And not just this library, any other library that kind of promotes this functional style of programming. Because again, if they're not doing things like saying shared data structures and they're copying a lot. This is just a pretty standard example that you could read in a lot of functional programming literature. And they're not using copy on write. You will see some slowdown over time, potentially, just due to the fact that you have a lot of in-memory copies and you have a lot of redundant information. And that, in and of itself, could cause some slowdown, especially as you're trying to allocate more and more memory. The other thing that you need to be aware of is, and this is a key goal of the FSet library, is some of these libraries and APIs tend to diverge from the core language design and principles that the language provides and promotes in order to, in a way, make it so that you are programming in a completely different language than the host language. That is not the goal of the FSet library. The FSet library is trying to make sure that it is well integrated into the host Common Lisp language so that it doesn't look out of the ordinary, so to speak. Finally, there is some goals that are related to space overhead and being able to deal with updates that we're going to have to touch base on. As we go through and explore this library, it will become more important. So one thing that I would like to mention before we get started is how are these core data types implemented? A lot of them, especially the primary ones, which we're going to be touching base on, mainly sets, bags, maps, and sequences, are implemented using essentially binary trees. So that means in terms of inserts and updates or even removals, you're looking at somewhat of a logarithmic time in terms of complexity when you're handling some of this. The trees are obviously going to be heterogeneous types, and they're going to be related to since they're balanced, you're going to end up having to you're going to end up seeing some, reduced space overhead than what you typically will see in a tree implementation, because balanced binary trees try to, optimize the depth and try to reduce the space overhead by trying to make sure that it's in the same page of memory. Now, I haven't actually had a chance to go look into the internals of this implementation, but I thought I'd at least mention some of the highlights of how some of this implementation was done. So let's get started here. The first thing that I want to bring up is how to use the FSet library. Now, from what I can tell is the FSet library has, for experimentation, a nice user namespace that we can use called FSet User. The reason for this is because and this is similar to other languages that provide a user namespace. There are some overrides in the way FSet handles certain operations, mainly maps and reduces, that conflict with the core common Lisp library. So if you're going to be experimenting or even using FSet on your in your real programs, just be warned that FSet reduce and FSet maps do have different meanings and different semantics than just normal reduce. So you can't just simply say reduce and expect it to get the right one. Now, obviously, my promotion when I tend to write code, and my recommendation to most folks tends to be, well, you shouldn't be trying to put this stuff in like the use category here in the package name if you're trying to use a library, but certainly it is. If you feel that you're always going to heavily use it, you could go ahead and do that and override some of those core operations just so that you could do it in your day-to-day basis. I just would like to know, when I tend to read code, just where a particular function is defined so that I can go quickly look it up, just in case there's a particular piece of code that I need to go in and debug. So this is going to, as we go through this and as we come up with examples, I'm going to introduce more and more concepts as to why this library really is, and its design goals really tends to be kind of the best choice of doing programming inside Common Lisp. But I just want to let folks know who are watching that if you have any questions during this, just feel free to post them in the chat, and I'll get to them as we as we go through some of these examples. So let me just do one thing here. Oops, that's not what I want to do. All right. So there are four main FSet types in the library. The first one is that we're going to be talking about is sets. The four types are sets, maps, sequences, and bags. Sets are obviously just like any other, usually any other implementation of sets is the same definition. It's an unordered collection of unique members. Okay, so you can, so let me just go ahead and write that down here. Unordered collection of unique members. And the one thing that that you need to realize is although this is what the definition is, there is some implicit ordering behind the scenes that FSet imposes, just mainly so that there can be certain optimizations done in some of the algorithms that use it. But at its heart, it's still going to be unordered. It's an unordered collection, and it still tries to maintain that characteristic. To actually use this, you would have to use the thought it was ISET Q image. This is okay. Let me see something here. Let me see if I could do that here. That's weird. Let's go ahead and check this out. So to get started on this, let's create an empty set here. I'm going to call this TestSet just for the sake of it, right? And I'm not going to use the ISETQ method for now, but you could certainly use this as well. But I'm pretty sure I could just do this if I remember my explanations last night. Okay, let's see if this works. All right, so if we look at what TestSet is, we will see TestSet's under. Oh, that's right, I'm in the wrong package. I have to do this inside the REPL. Let's go ahead and do that. All right, if we look at what TestSet is, you can see that FSet provides a nice reader macro for you to be able to, read through this particular thing without actually seeing a full-blown object behind the scenes. And you'll see this even with, say, a case for maps, bags, and sequences. But I just am merely mentioning this for completeness sake. If you wanted to add to this, you could certainly do so by using ISETQ to actually go ahead and modify an existing set, or even use an existing set to actually go in and copy it over. Now, if you're trying to join or add within an existing set, though, you have to use the with keyword. And again, I'm not using FSet colon here just because I'm in the FSet user package, but I thought I'd just at least bring this up here. And you could use that, provide the test set, and then add to it, and then you'll end up getting a new set that's 3. And you can see that this is a new set because if you do test set, you'll see that the test set is still empty. This is the first thing that I wanted to kind of bring up. Now, if there is if there's a predefined set that you wanted to obviously create, and let's create another parameter, another global parameter, just for example's sake. And you want to provide a set with some predefined numbers, then you could do, if I remember correctly, set, and then provide the 1, 2, 3, let's say 1, 2, 3, 4. Actually, let's go with that, so that way I could show intersection and union. And you'll end up getting, a pre-populated set. Now, this library provides, again, because it's trying to be functional, it provides a bunch of functions with set theoretic operations. You saw some of that already when I, when I went to FSet colon and I did set. One of them is set difference and set difference 2. Now there are, I'm still not entirely sure what is the difference between those two particular functions. I'm still going through the documentation on that to try and see why there's two different set differences, but I'm just showing you there's also set intersection, set union, adjoin. There's a bunch of core ones, and we'll go through each of them as we explore this library. To check to see if a set is empty, you could just use just like scheme, you could use the empty predicate with the question mark and determine whether or not a particular set is empty or not. That's one thing that I'm going to bring up about one of the designs and some of the APIs that FSet provides. It provides a lot of these operations in a very scheme-like fashion in terms, and it adopted some of the scheme-like practices for predicates and things like this. So don't be entirely alarmed when you see question marks or bangs or something like that, and you're thinking that, oh, they adopted or they implemented scheme. They didn't actually implement scheme on top of Common Lisp. This library is not that. That is not its goal. Although you could certainly do so if you wanted to. That is not what the goal is of this particular library. I'm just giving that heads up because when I first looked at this, that was the first thing that came into my head, and that's certainly not the case here. To illustrate some of another thing that we can do is some of the operations that we can use in the FSet that may not necessarily be entirely related to some set theoretic operations or functional operations, but some things that are useful. I'm going to show you one function that I've never seen used in this way, but I know you can implement it in other languages that implement sets like C++, and that is the arbitrary function. ARB basically takes a collection, particularly in this case a set, and if it's non-empty, it'll randomly give you one of the members. So I have only 3 members in another test set. If I use arbitrary, it might give me 1. It might give me. Should it? So one thing that's happening is, and this is particularly interesting, is the documentation states, and I haven't that arbitrary is giving you a it's supposed to give you some member of its set. Typically, it states that most people might be thinking, oh, it's always going to give you the first member of the set by this behavior that you're seeing here. But it's not. That is not its guarantee. It doesn't guarantee that. And I was trying to demonstrate that, but it also seems like it doesn't guarantee random selection. It just guarantees that it's going to give you something from it, which is kind of weird. I don't know why they would provide this function. In C++, for example, you can use random shuffle to actually go and grab, a particular member, or shuffling a particular S collection and grab its first member, and it will do it in a copy-oriented manner if you provide another collection type too as well. That's why I was trying to illustrate that here. The other thing that you may want to know is how to do set removal. So I've shown you how to do set addition, which is with S. With the with keyword. With will take in a collection and some value and give you a new set. Obviously, then the logical next thing is how do we remove something from a set, and that is simply by using less. Less is actually just going to go ahead and take in a non-empty collection. And if it's empty, it doesn't do anything, as you can see here. It'll throw up an error. Sorry, that's the wrong thing. I realized what I just did. It'll just return the empty set because it's already empty in this case. TestSet doesn't have anything. But if you have a non-empty set that you see here, it will return the set without the operation remove. Now, again, I'm going to reiterate this, and I'm going to keep bringing this up throughout this presentation. S is actually not modified. The return value is always going to be a new collection type. So you're going to end up, if you're creating a lot of temporary collections, this is going to potentially give you some sort of space overhead if you have, just because you have a lot of garbage, and it's going to potentially cause some performance issues. But based on my current day-to-day use, I haven't actually hit that or stumbled any sort of situations where that's going to become more of a problem or not. Obviously, the other thing that we'd want to take a look at is the size of a collection, which you can use FSet set size. No, it's going to be FSet size, and it'll take in a collection type, and it'll give you the number of operations. Set size is for bags. That's a different thing that we're going to be discussing later on. But let's quickly let me just quickly write out here the things that we've seen so far, so that way folks can use this for their reference later on. And that is adding members with the with keyword. That is, and you're using FSet Q. Actually, that may not work here, but we'll see. Yeah, that's what I thought. So I can't do that. I have to do this. Def parameter. Addition. So this. Oh, sorry. There we go. I'm just switching us over to the def package right now for a minute. For the FSet intro, just so that I can just check something. Okay, yeah, it works. Then obviously we could just do check if empty with the set empty. You can remove a member. And that is, let's say, member example. Just do this, and we'll say FSet plus. So I'm trying to show you two different ways of using this. Now, the FSet Q stuff that I've been using so far, that works well with FSet User. If you're in the FSet User package, so if you end up in your package, in your Lisp package, your custom defined package, like up here on line 2, if you end up saying that you want to use FSet User, you'll end up having access to some of those APIs. I discourage that just because it might hide some pernicious things. It'll be better just to go ahead and approach it this way, which is using standard common Lisp for the declaration and definition of your variables, and then just use the exposed API from FSet itself to actually create your variables and so forth. Just another construction. Create empty set here and create a set predefined. And the way you do that All right. So now let's talk about quickly the set theoretic operations here. Did I miss one more function here? I'm just making sure I didn't before we get into that. Yes, there's one more thing that I should briefly mention. That is, technically there is a constructor macro that can be used that can take in a set and includes all the elements of that set when you're creating a new set. This isn't actually union, but I wanted to show this one specifically just because it allows you to write a shorthand syntax to take in members of one set and put it into another set without actually doing an explicit union. The way we use this is we do FSet and we provide set. We still use the predefined set, but here what we do is FSet $, all right? And you can see that if I can actually, for some reason, it's not. Let's see if this works. We'll take in the predefined set, and let's say that we put in another variable, and we do that. What happens is you get a new set here that has a new member associated with it. You cannot actually use this constructor macro as is, as far as I know. You can't actually use it outside of the FSet :set call. So for folks who attempt doing this, you will get an error. It'll say that it's undefined, but you clearly can see that it's necessary. It allows you to write something like this here and create another set. So this is another way of adding members to a set. Use constructor to also create new sets with members. And I'll go ahead and, put a definition on this. All right. Let's talk about set theoretic operations. Yeah. So most set theoretic operations you may be familiar with. Obviously, union, intersection, set difference. There's also technically complement, but I don't believe complement is here just mainly because that you can use set difference when you're doing a complement between two sets, and usually complements tend to be a much larger uncountably infinite set that cannot be represented or cannot be generated in a quick amount of time. So I'm only mentioning it here because folks who are watching who are wondering where complement is, it's not an actual useful operation for day-to-day work. So to begin with, the first thing I'm going to show you is obviously equality, and then we'll go through some of the set theoretic operations. Equality is a pretty simple thing. You can check to see if two sets are equal. You have this equal sign. You provide two sets. Let's say test set and predefined set. Obviously, these aren't going to be equal. So if we print the equality of this, you'll see that it will print nil. If you say, FSet equal test set, because it's the same set, it's going to be, this is going to be true. Additionally, you can use equality, and it's not doing a strict EQ. So you can see that this is doing an actual proper equality. So if you end up saying something like this, you'll see that it's actually looking into the internals of the con cell, or the object itself, to make sure that the members are equal or not. Then we have the actual union of two sets. So in order for us to do this, let me just go ahead and create a let form here, and create another set that has 4, 5, 6. Okay. If I try to, and actually let me put 3, 4, 5, 6 for example purposes. If I create the union of this set with our predefined set, you will see that it will remove that duplicate, just like any normal set library would do, and give you 1, 2, 3, 4, 5, 6. We also have, set intersection that will take. Now, for folks who are looking at the mini buffer, you might see set or bag or collection. So some of these functions are generalized to actually work on all collection types that are provided by FSet. Some are not. And you need to look at the actual signature to make sure that you're getting something that is a collection-based function, or a function that is very specific to a subset of the data structures that are provided by this library. Let me see. No questions. All right. So here, if we do, obviously, if we do predefined set here, and another set, and just to make things a little bit simpler, let me go ahead and let me do one thing. I'm pretty sure I could do this. This will do a concatenation. Nope, I have to actually do this. Okay, I'm going to go change this to a format so I can actually add some formatted strings here. Okay. All right. This one is going to be our set union. Set intersection. I'm just making it so that it's easier to differentiate between them on the command line. Obviously, they will be in sequential one after the other, but when you're reading it very, very quickly, you might end up getting confused. All right, and if we do that, you'll see that in our set intersection, obviously they found the commonality between the two. Now, set difference. Set difference is if you do A minus B, that's where A and B are two sets, it's going to give you all the elements in A that are not in B. So this should give you 1, 2. If we do FSet set difference or predefined set. There we go. And for folks who are looking at this, just for completeness sake, this is, if we do it the other way around, here, B minus A, you will end up getting the opposite of this, which is 4, 5, and 6, which is showing you that set difference is not commutative. It's not a Oh, sorry. If I actually switch the arguments, you'll end up getting there we go. So that way I don't. All right. So I showed you set union, set intersection, set difference, but then you may have noticed this set difference 2. All right. And for that, I'm going to have to show this because I'm not entirely sure what this will give us. A minus b, that, and let's do that. 2. This doesn't look like it's giving us anything different, but I think it might be giving us multiple return values. So let me just make sure. Let set b set 4 5 6. Okay. So if you wanted to actually get a minus b and b minus a both in one fell swoop, instead of doing what I did, which is 2 calls to FSet difference, this guy, that's why I didn't see it when I was looking at the difference between the two. This guy will actually go ahead and give you both directions. It will give you a minus b has the first return value and b minus a has the second return value, so you can use multiple value binds. This will be used for folks who are looking at this and wondering, well, when will this kind of function will be useful? It's particularly useful if you're doing like relational algebra and you're trying to get a projection, and this is giving you an outer join essentially between the two sets. So it's this is it's a partition. Judd, could you be more specific as to what your question is? Not quite.
Yeah, so these two subsets are just the disjoint subsets of the union, right?
Right. That's correct. That is correct. It's kind of, and you can see that you can actually stitch that together because you're essentially getting the same return values when you're calling set difference twice. This is one single operation to do both to essentially give you the result that you wanted, which is a disjoint set of the union.
So there could be some function that you use to maybe select, right? To select things in set A, and then you could just say, okay, the ones that match and the ones that don't match.
Yes.
The ones that match you list out, and then you go, okay, give me the differences. I think. I mean, I'm clear on it.
Well, one way of using this is if you're doing, you could. Let me try doing this. One way I would use it is I would, instead of what I did here, where I took set difference, what I'll do is I would, if I was trying to look at what the differences were between two things in two different sets, I wouldn't just use set difference. I'll just use multiple value bind on disjoint set 1, we'll call it. DS1 and disjoint set 2, DS2, on the call to FSet difference to grab this information and then do some additional analysis on it. So this way, I don't have to actually do the symmetric operation because you notice I actually had to switch the arguments when I did it the other way. Here, it'll do that for me. It will take that single call and give me exactly the disjoint sets that I want. So I don't have to think twice about where one is versus another. And this is, again, this would be useful when you're starting to deal with sets of particular characteristics and you're doing like a relational style code and you need this information. So let me just complete this example. So you'll know DS1 that T A minus B is this guy, and B minus A is this guy. And you get the same result. All right. So the final thing that we should talk about is just an obvious thing here is are there predicates for dealing with, since Judd actually mentioned it, disjointness and subsets. And for that, there is actually one way of actually showing that example. There are ways to actually to check for disjointness and check for a subset, if one set is a subset of another. And for that, I'm going to create a quick example. I'm going to create another let form of a subset of TestSet. Okay, and I'm also going to create a disjoint set of TestSet that has members that do not obviously belong to it. The way that you could check to see if one is a subset of another is through, obviously, subset with a question mark. And this will take in two arguments. The first argument, so it reads left to right. Is one a subset of another? So is A a subset of B? This matches kind of like the notation that most people tend to write, which is the rotated U with and the only time you ever put the underscore, I'm sorry, not the underscore, the line underneath that is when you're dealing with equality, so they could be the same thing. I know that if you do this, okay, and we provide our predefined set here, you will end up getting a true. The one thing that I wasn't sure of, but I may as well check, is what will happen if we do set is a, this is a dumb test, but this really is saying that they're equal, but this also is technically true mathematically, because for most of you who are familiar with sets, know unless you're saying that they're proper subsets of each other, a set is a subset of itself. So this should also return true. So if we look at that, you'll see that you'll end up returning true. For disjointness, So that means for folks who are looking for proper subsets, this predicate does not give you a test to see if something is a proper subset. You could certainly do that by doing essentially, the following, which is you check to see if the set difference between two sets is empty or not. So here, another set and predefined set here. If actually it will be the other way around. It will be predefined set and then another set. So this is the superset that you're trying to subtract from the subset. You're going to subtract a subset from the superset, and if you end up getting a non-empty set, then that it means then the subset is a proper subset. And you could just go ahead and do this. Here you'll see, here you'll see that what's returned by empty is nil. It's not empty, so that means that it's not it's a proper subset. So you can actually go ahead and let's define that proper subset. It takes a super and a subset, and what it will do is it will return what we just did here. Right, and obviously this should be knotted because it's a proper subset if it's not empty. Stall warning. Oh, that's right. Cut super sub. There we go. Proper subset. Predefined set. And I'm going to go ahead and change the notation here so that it actually matches our FSet notation and we don't get confused by it. Subset, another set, superset, our predefined set. And you'll see here, it's true. To check if two things are disjoint, FSet provides a disjoint, set. You'll take two sets here. Let's say here we have our disjoint set that we wanted to test against, and our predefined set. Actually, we don't even have to use a predefined set here. We'll just go ahead and use another set here. And since 1, 2, and 4, 5 are clearly disjoint from each other, this will give you true as well. So we've now seen subset. We've now seen that technically subset question mark for sets inside FSet does not provide. It does not require the set to be a proper subset. You saw how trivial it was to add proper subset to the library just because it is just built on existing things that are provided by FSet libraries, and we added that into the FSet thing. But notice the entire time, if we at all test predefined set, the sets were not modified. And this is a key characteristic for functional collections that only common Lisp lists that are created with cons provide. Vectors inside common Lisp also can use some of the functional collections too as well. But that's because vectors and lists are both subclasses of the higher level sequences, which is what is the basis for most of the algorithms that are inside the Common Lisp library. We'll see, though, three data structures that are provided by FSet that clearly does not, allow you to, work with in a functional style manner. Sets is one of them, and the other three that we're going to be covering is maps, bags, and what they call immutable sequences. But I'm not entirely sure what the difference is right now between those two. Are there questions? Okay. So the next thing that we're going to be talking about is maps. Now, apps are obviously, it's an implementation of a hash table inside inside FSet. To create a map in FSet, you have the let me call this example map. Okay, you have the FSet empty map function. You also have the ability to add to this in the same way that we did before. It'll create a new map. So let's go ahead and call this populated map. So this is a map with some predefined set of key value pairs. You can use the with keyword on an empty map. And then the way you add to this collection is it acts like a plist. So the first thing that you provide is the key, and the second thing that you provide is the value. And what ends up happening is, if we look at what populate map is, you'll see that it creates, and again, the reader syntax that is provided by FSet, a map where the associated pair is x:1. So for folks who are used to plists, this notation should be familiar to you. There's another way of actually defining a map, if I'm not mistaken. Another populated map. That is. And that is with FSet map. And you can provide x1 here. And this, did I mess that up? All be pairs. Okay, that's right. That's right. This needs to be a pair. Oops. Give me a second. Do I have to use the FSet $? Maybe in here? Maybe that's probably why. Oh, sorry. FSet. Okay. I'm messing that up. Let's see if I can do this. 2-element list. I'll figure that one out. There is one weird thing. I swear I've seen an example where you could do a to notation thing, but I don't want to spend too much time on this. I'll put this on the final thing just to give you guys a heads up on how to do it the other way, because there is a way of where instead of using this, because as folks watch and probably are noticing, the first thing they'll say is this pre-population syntax, although useful for adding new things to existing things, does not really work for if you're trying to construct a populated map from scratch upon like initialization. There must be an easier way. And there is an easier way by using FSet map and pass in a set of pairs, but I think I'm messing up the syntax right now. And oh, that's it. I think I got it. That's it. It doesn't. So most people who are familiar, this is just a quirkiness of the way FSet provides its object constructors, and it threw me off the first time I looked at this. But basically, when you're passing in a pair for most of the standard common Lisp functions, you have to quote it. Otherwise, it treats that as an S expression and evaluates it. But FSet map does not evaluate these, and it treats each of these pairs as individual, like actual pairs of key values. So if you end up doing this, this is treated as a 2-element list, rather than a S expression where the first argument is a function call. So that's a little quirk that I'm going to mention right now that that's ignored by FSet when it's actually parsing the arguments, and it will give you that list pair. So if we look at this now, and we look at another populated map, you'll get, and obviously here, 2 keys and values. Now, it does do an implicit sort just like any other map behind the scenes in a hash table. Here we're doing lexicographical things. You could provide, like, here, another thing in order, and it will give you, if we look at, look at another ordered map, it'll sort the actual key value store based on the key that it provides. Now, to look up a particular key in a map, we can use 2 different functions. One is FSet lookup, and that takes the collection that you provided. So let's say here another populated map, and we provided the key, and it will go ahead and print the value for us, as you can see here. There's also if you actually implemented this with multiple value bind, FSet lookup actually returns 2 values. It'll return you the value if it exists and whether or not the key was found. So for folks who are who write in languages like Go, for example, this is a common practice that is used in Go. I've seen also in some common Lisp libraries adopt this too as well for multiple value returns, particularly for key lookups. Just not as often as I thought I would. But basically, if you end up doing value found here and you do FSet lookup, you can actually say when found print val. And this will return 1. Obviously, if we change this to C here, the code will not execute because found is now nil, and obviously that means that the code to print the value is actually skipped. So you can use this to defensively code to make sure a particular key is actually inserted, and then throwing appropriate error when you need to. Now, FSet lookup actually has a macro, a reader macro that you can use too as well, and I'll show this to you here. And that's FSet @sign. This will take in a function or a collection, a particular argument here. We'll just go ahead and populate that with that, and we could provide X, and it will give you the same thing. It's the same as calling a lookup. Now, if we provide C here, you can see that nothing is there, so it will return nil. There's also an ability, for example, for you to change the default when the key is not in the map. So if you're not used to, if you want to use some other value other than nil that's provided here, you could change it by using with default. So what I mean, and I think the easiest way to do this is a common example. Most of the time, a lot of folks would write something like this: @sign, another populated map C, and then if found, we'll print something. Otherwise, let's print 0. All right. This code obviously will, if you have to add this for every case where a default value is necessary, that will become a little unwieldy, right? So what FSet provides is this ability. Let's go ahead and change this in a new map structure, which I'll call populated. Well, let's call it KV store, for example. And then what we'll do here is we will use the with default keyword, the with default macro, which will take in a collection, all right, and it allows you to provide a new default, all right. So that means, let's say that this is going to be 3, all right. So now what's going to happen is let's go ahead and ignore the found for a second, because I don't think this is going to be needed anymore. And instead, we'll just print val, all right? And what I'll do is I'm going to show you 2 cases. Obviously, this doesn't need to be a multi-value bind at this point. Let me go ahead and change this guy here to UB a let. So the first case is obviously, let's go ahead and grab the value of something that is already in there, say X. This eval at kv store c. Okay. So the first case is going to be obviously the value that's already in the map, all right? But you're going to see something different in the second case, in the eval case. And that is, it's going to print out 3 instead of nil. With default gives you the ability to provide some sort of default value for your collection types in the case that keys don't exist inside of it. This is equivalent to many map libraries where if you don't want to use the optional argument, because nowadays a lot of maps, especially collections library, now that most modern languages have optional types, what they normally do is they give you the ability to it'll return you the optional, but they have also additional functions in the API that'll give you the ability to return some sort of default value in case that the optional is null or it doesn't exist. So that's the equivalent here that you're seeing with default. Folks who are wondering why this couldn't be just a simple function call, this is pretty useful because this with default is only dealing with modifying a new map structure with this default value. And I could show that to you by simply doing this. If I do now FSet at another map, populated map, see, you can see that the another populated map still has not been changed. And it again goes back to this reiteration that these are functional collections, these are immutable collections that you're going to be dealing with all the time. Now, the rest of this stuff that I'm just going to bring in is maps have the same functions as sets do in terms of union, intersection, and difference, but their function calls are slightly different in terms of, instead of being, since maps and sets don't necessarily, well, they're not rightfully belonging to the same sequence type, maps end up having their own set of these set theoretic operations. And to show this, I'm just going to quickly create another map with C4 D5 E6, right? Boom. So now let's go ahead and print map dash union of another map and a map. And then we're going to also look at the map intersection. And I'm going to go ahead and make this a E3 here. Map intersection is going to take in 2 maps and actually return you the key value pair that's in both of them. It's not going to be looking at just a value or just a key. It's going to be both. And that goes back to what I was saying. Maps, behavior-wise, are very much like p-lists when you're looking at them. Then, like before, we have diff1, diff2, which is our difference to another populated map. So this is the it'll give you both. You have map difference, which will take in two maps and give you the difference of one versus the other. And here I'm just showing you that this will give you b minus a and a minus b at the same time, just like before. So now, a single call, you end up getting both what's in another populator map that's not in a map and the other way around. All right. Let's talk about very quickly, and I'm hoping that you're getting a sense here as we're going through FSet and these sequences and what's available inside of this, that the actual design is very, very consistent in the collection types that are available in the FSet, and allow you to very, very quickly be able to use this library to implement your algorithms very consistently across your code base. And additionally, given the fact that these are shared underneath and they're immutable, most of the data structures are immutable by default, this will encourage you to create a function library that's compositional in nature, that will allow you to build up pipelines that will work on these kinds of data structures as they come through, and allow you to essentially at any point in time grab any of them and audit those data structures, because you'll know for sure that once they have been set, they're no longer going to be modified again. And that's a bit liberating when you're actually going through and having to audit particular pieces of code. So I'm going to just quickly introduce this one thing, and then we'll touch base with sequences a little bit more in bags. But I'm going to just talk about seeks, because I think it's important to understand the differences between what seeks are and what's provided by Common Lisp. To begin with, let me talk about Standard Common Lisp. Standard Common Lisp has lists and vectors, and ultimately lists and vectors are both actually, using the O vernacular, subclasses or subtypes of this higher level type called a sequence. Now, you may have read somewhere that there are various proposals that are out there and various third-party libraries that have implemented these proposals. But basically, sequences themselves don't allow you to create user-defined sequences, so that you can actually extend the sequence types that are available and use the standard Common Lisp functions against these. You only have two options right now today, which is vectors and lists. Unless, and I think most of you already know this, but I'll just bring this up anyway to be complete, unless you're using SBCL, because SBCL has a system extension that allows you to do user extensible sequences. I won't touch any more on that today, but I am mentioning it because it is an option if you really need to define certain sequence types, and if you restrict yourself to SBCL, you have this option. So what Seek provides in FSet that's slightly different is it is consistent in terms of it itself is also a sequence in FSet. And like Common Lisp, it is zero indexed, unlike most sequence types in like one index languages like Pascal or Modula or Oberon and so forth. Or even for folks who work in the numerical space, there are languages like Mathematica that also do natural-based indexing instead of zero-based indexing. But the semantics of the sequence that's only different from the sequence type that's provided by Common Lisp is that FSet sequences are in and of themselves immutable. That is, and that should obviously raise red flags for folks, because I did mention earlier that you could work functionally with lists and vectors, and now I'm saying that, well, these are immutable by default in FSet, so how are they really, really different from Common Lisp? Well, technically, common Lisp sequence types, you can modify the collection at a particular index by using aref or setf to an aref, and then you can go ahead and modify that particular vector. In this case, you cannot actually modify the actual vector itself. You can, and just to show this, immutable sequences, we're going to start with our standard empty sequence, which I'll call empty seq. And empty seq is also the name of the function that you use to create one. And if you look at the empty seq syntax, you'll see that this is very much close to the reader macro that if I remember, on closure, on how seqs are represented. Once you have that, you can go ahead and add elements to it with the width keyword. But before we do that, I'm also going to provide a parameter. Def parameter. Thank you. Simple. That you can also do seq, and you can provide arguments to seq here. And we'll create it. Now, just like common Lisp sequences, seqs in FSet are heterogeneous. They don't have to hold parameters of the same type. They don't need to hold data of the same type. If you actually go and look at this type of seq example, you'll see that it is actually of this particular type. Now, if we end up saying that we wanted to look at, for example, type of FSet seq 234, there might be cases where they'll do certain optimizations, but for the most part, they'll all be of this type, the WB seq type. This is a pretty wide-bounded seq type, but I'm just letting you know that that's kind of the type that you're dealing with. Once we have the ability to construct these, obviously the next step is to be able to, inject them into a particular thing like before with sets, and that's where FSet seq's constructor also allows you to use the same dollar syntax that we used before, and you can inject your entire contents of one sequence into another sequence. So here in this example, if I go in and look at a seq example, you'll see that it created a new sequence type that contains all the contents of this sequence as well. You can also add sequences just like before, which is, FSet width first and width last. So the difference between width first and width last is where you're actually appending it. So if we do our is equal example, and we provide, go ahead and do this. For and we do that. We paste it. We'll end up seeing that it's in the beginning. If we change this to with last, it'll append it at the end. This is for, if you're switching between, if you want to mimic using a stack-based or a queue-based kind of like functionality, this is with first and with last. Similarly, to remove elements, you have the ability to also call less. That's the FSet library notation for what removal is. You do less on seq first, and then you'll remove the first element. Again, sequence is still not, modified. It will always return you a new sequence. Last is also the opposite of that. It will remove it from the end. Finally, there's also, the ability to check, to grab the first element of the list or the sequence here, and the last as well. These are providing you multiple value returns, so you could check to see if something is empty. If you pass in an empty sequence, it's going to give you nil by the default as well. And this is the same for if you pass it into last as well, to check if something is empty. So this way, you don't necessarily need to access a value. You can always check the Boolean that's returned as a second thing through multi-value bind, and use that to verify or throw up an error if a particular thing expects something to be empty or not. Now, since these are immutable sequences, you can use these as quick lookups tables, and you could do them based on indexes. And the way you could do that is using just like you would use what we showed earlier with maps. And you could provide sequence example, and you could provide an index. So let's say that we want to grab the second element of our sequence example, which is 2. It'll go ahead and return you something, but you could also use this to check to see if something is not there at all. So if you'd use the empty sequence, for example, here, and you provide some random thing here, instead of blowing up and giving you an error, what it's going to blow up and what it's going to do is it will return nil. And it'll tell you nil has the actual argument as to what's available or not. Okay, so there are a couple of other things about sequences that I would like to discuss, but I'm not going to. I'm going to go ahead and stop now. I'll open the floor for questions for folks watching, and if not, we can. If you guys are okay, we could just I could just finish up this exploration, and we can touch base on bags next week. Okay, there are no questions here. Any questions from folks who are on the Hangout? All right. Okay. Just two final things on seek types, and then we'll be done here. And that is like maps, lookups have their own problems. If a lookup doesn't return something that actually exists in a particular collection type, we may want to have some ability to provide it'll extend we need to have some way to provide some sort of default to the collection type, so that we can return something that we can easily compare to instead of just nil. And the way we could do that is just like before. We can call FSet with default on the collection type. And again, not all collections provide you this ability. Some collection types may not. I know sets you can also use this as well, although we did see this with maps. I haven't tried bags with this. I think bags will allow you to do this. So most of the primitive, if not all the primitive types, support this ability for you to be able to provide some sort of default. So let's say that we make that the new default. And now let's go ahead and print, print FSet @ ASet 4. This is obviously out of bounds, so there's nothing going to be in here. Instead of ASet, I'm going to call this seek, just to make sure that there's a difference here. And you'll see that just like before, it is a -1, and just like before also, if we try to call that same thing on seek, you're going to end up getting a nil like this. Seek types have something particularly interesting. Before, we saw that we can actually insert into a seek type by simply using the with keyword like this. And you could provide, multiple values here. It only allows you to, it doesn't do like a rest argument. I don't think you provide like more than 3 values, at least more than 2 values, because at least based on the mini buffer signature as you see here, it only allows you to do at most 2 at a time. So if you do this, this is going to be throwing up an error. And you can see that it will return. Usually what FSet does is it will use this to update your seek sample if it recognizes that it matches a particular pattern. So like you saw before, just to show you this is what our seek example is, 1, 2a. What's returned by FSet with what I just did is 1, 7a. So we just essentially used the with keyword to go in and remove 2 and update the first index the second index in that collection with 7 instead of 2. So this is one way of using with. With actually, more specifically, updates an element at a specific index. It can also be used to append. Now, what you could do here is you could also use, if you want to, since all these are randomized collections, you can also use insert to take a sequence. All right, it'll take a particular index that you want to insert at. Let's say that we want to insert a 7 between 1 and 2. And you could provide some value. And what it does is it will actually return you a new sequence with that value appended there. It'll essentially create that type, that new sequence index with that new value being in there. And again, just to show this again, sequence is not modified. It's a brand new sequence. In fact, if you end up using with, you could also use with to also append to, sorry, not with, just in the same way that and this will give you something that's at the VV. So far what I showed you is we're able to use with to update a particular index. Okay. I showed you that if I provide the first value here is treated like an index here. So with, if we do 0, we'll end up removing a 1 and provide 7. Here we're doing 1. Here we're doing 2. Okay. Here we're using with to append at the end of the collection because we know that this has 3 values. We're going to go use the first argument for with is going to be the index into the collection that you're trying to modify and stuff. And in this case, 3 is at the very end of the collection. We have 3 elements. This is going to be the 4th element. So it recognizes that and it will go and append it, right? But what if you give it a really bogus index, all right? So let's say that continuing on our example here, let's say that instead of 3, we gave it 7, okay? Has the index to add B. There's only 3 elements in sequence example, right? What is going to happen now since we gave this one that's really outside of the ordinary, and the sequence type hasn't grown to that size, right? What it actually does is it actually goes ahead and fills it for you with some default value. All right. It recognizes that they don't exist, and it will provide some sort of default. Usually nil is the default, and it will go ahead and dump it, right? So obviously here, this is where with default would come into play, very, very useful. What you may want to do is use the fill pointer to be something than nil. And so you might want to do something like this. Let's go ahead and grab that, paste that here, do that. Change this to a sequence. And you'll end up getting a new structure with the new default. All right, and you may notice that there's a /0 there. That /0 that you see at the end for this new with default that we didn't see before when we were using -1 is it's basically telling you what the default is. So if we change this back to nil, would this work? No, because of the fact that since it's nil, it recognizes that is the core default that you used before. So anything other than nil, when you're doing updates to a particular data structure, the actual REPL will give you recognition that you changed the actual default, and it will tell you that the reason why 0 is there is because the default has been changed. Okay. Obviously, what's left? I talked about updates to a sequence. I talked about inserts and appends to a sequence based on it. I showed you that you can use this sequence types much like you would use closure sequence types to actually go and modify particular structures. The only thing left to show you is removing something from a sequence and then concatenating 2 different sequences. So removing is just like before. There isn't anything new here. You just use FSet less. You can provide your sequence. You provide your value that you want to get rid of. And if you print this out, you'll see that you removed 2 from the actual sequence. And the reason for that is, and it goes back to what the sequence type is, a sequence is an indexed collection. So the argument that you're providing, the first argument that you're providing to any of the collection APIs when you're passing in a sequence type is the index in the collection that you want to go and modify. Either or manipulate. Okay, so either you're adding something into it or you're dealing with it. To concatenate 2 different sequences, we can use FSet concat. It will take sequence 1, let's just go ahead and make sequence 1 our sequence without 2, and let's combine that with the sequence without 1, and what we'll get is 142A. And it'll allow you to go ahead and manipulate that. We also have the ability to use subsequences. We could check to see. We can actually provide some level of subsequences, and I'm going to go ahead to do this. I'm going to quickly create a very large sequence here. If you just bear with me for just 1 second. If I remember to do this, it would be what is seek. Let's go ahead and do this. This is going to be a little disgusting. I don't think this is the right way to do it, but I think this is the best way to do it for right now. Do times x10 set of. I don't think this should not work, but I think I've done this before and it does work, because these are creating a new sequence every time, and we're creating a seek with x and a seek. Oh, right. To do this, we have to do FSet size a seek. All right. So this is a little disgusting the way I just did this, but that's only because, again, like I said, I'm still getting used to how to do certain things in this library. But I threw away essentially 9 copies of the seek type by doing it this way. So a lot of unnecessary garbage being created this way, but it's probably the best way to do it right now, in the case of time. So I have this populated set now. If I want to grab, say, the subsequence of this guy, I could pass in subsequence. I could take in the sequence. I give it a starting index. Let's say that we want essentially 2 through 7. So this is, if I remember correctly, it is an inclusive interval. So you provide it the start index, not to the start index, and then the ending index that we want, which is I think it's 2 through 7, and shoot, just do that. You end up getting, so I was wrong, it's not inclusive, it's a half open interval. So that's the other thing about a lot of FSet stuff that I'm going to bring up. Most FSet sequence types that are dealing with index collections are half open intervals when you're dealing with the start and the ending bound. This is very common for most zero index based things. Sometimes, like if you remember in in some of the standard common Lisp data structures, they are inclusive. That's not the case here. So you provide a lower bound, and it includes this as the first element, and your end is the last index to cut the loop. So it's going to be excluded from the actual final result. There's other things that you could use, but I'm just going to mention this final piece, and then I will close this off for sequences because we'll be done. And that is although we have these immutable sequences like this, most of the standard common Lisp library functions like find, print, find, one, in sequence example, and are available at your disposal. What? That's not true. Well, it claimed that it could do it, and I thought I actually saw this work for an example. I may have used something that it supports and others that do not. Let's see something else. It's not of type sequence, but it is of type sequence. Just added some additional functionality. Oh, well, you have seen this, folks. I will ping this. This looks like an issue. I will go ahead and post. I think we just found ourselves a bug here. If you're reading documentation, the one thing that sequence types I thought were pretty neat that made them really more useful is FSet seeks, I thought, were generalized immutable sequences that you can use CL operations. And this is the first time I actually tried checking this out, and it looks like that is not the case. So folks who are trying this out, just fair warning, seek types, although they're claimed to have that, it does not look like that is the case. Let's just make sure that this works with this 1, 2, 3, 4, 5. Yeah. The problem is that. Let me see if they change this, though. That's the reason why. I have to use the equivalent. Let's see this. There it is. So FSet has, and this goes back to what I was saying earlier, and I just forgot about it. I thought it was just reducing maps. FSet provides all the common Lisp generic operations in the FSet library, expose library. If you want to use positions and stuff like that, you could certainly do so. You have all of the generic operations at your disposal, and it will go ahead and create new stuff for you. So my recommendation for folks who are watching this is if you're going to end up using FSet, just stay within FSet. Don't try to do combinations between FSet and standard CL, just because the fact that, like you saw earlier, what I was doing here. When you read certain things, it might say that, oh, this is not available or this is available, but if you use CL : the equivalent, it's not going to work. FSet changed some of the syntax and semantics of some of those generic operations to make it easier to work with their core primitive types. So just a fair warning on that. And with that, thanks for all of you that are watching and sticking around. I do appreciate it. And I will next week we will finish off FSet, and there's going to be another library that we're going to be talking about. So let's I'll bring that up as a surprise next week. So I will see you guys next week. Thanks.